So the second application that I would like to mention is about image processing and compressive sensing. When I was a graduate student, I encountered this type of picture, and I was like, so why do we need this? Is it like mixing different pictures just for fun, or what are you gonna do with it? But when I moved to industry, I actually learned, okay, this actually makes perfect sense. So on the next slide, you can see how we do image processing. For example, we have a nuclear magnetic resonance image of the subsurface at a certain depth, and this picture on the left, you see it's called T1, T2 map. And different fluids have different T1, T2 maps, and you can actually make a judgment on the shape of the fluid, where it is located, what are different coefficients equal to, and you can make a conclusion whether you have oil, whether you have water, and also there are different types of oil. Some oil can be very tight, it's impossible to pump, but some may be free oil, so it may be used for estimating the amount of oil under the surface. And I did quite a lot of work in this project. The real pictures look even more complicated. You have some very blurry pictures, mixtures, and we apply image processing techniques to separate different images and estimate volumes of the oil. So it is a very promising approach. Next month I'm going to travel to Oklahoma, to Tulsa, to present this work to my students about NMR, nuclear magnetic resonance applications in oil and gas. And we're going to write a paper on this as well. And the last topic that I work a lot is about seismic data. It is compressive sensing. It's actually very easy to understand because it all starts with linear algebra. For example, you have a system of linear equations, ax is equal to y, and you have a matrix, right? So you can say, okay, so what do we know about A? If it is a square matrix, if it is invertible, we can solve it. We can solve the equation. And well, it depends on the rank of the matrix and the right-hand side as well, but it's something very straightforward. However, what if the number of observations is much smaller than the number of variables? So you can say, okay, we have m equations and n variables. What are we going to do? Well, very likely this problem has infinitely many solutions. However, well, in reality, you don't want infinitely many solutions. And you can look at some optimization problem. For example, you want to solve the equation that is not exact equation, but is satisfying some condition that, for example, the difference between the right and left-hand side is bounded by some noise level, because that's the reality that your data is not precise. And then you say, okay, we want some constraint, or there are many ways to formulate this problem. We want to minimize certain norm of the observations. Oops, do we have a... Let me see. Do we have a sound?
We hear you.
Oh yeah, awesome. Yeah.
Go ahead. Yeah.
Okay, thanks. Yeah, so for example, if you know something about the signal that most of the values of the variable are equal to 0, for example, then it reduces to optimization problem. And it is a very interesting topic. I'm reading books about it in my spare time. There are some other applications. In the next slide, you can see some reconstruction of the seismic data that I was doing. I used the ideas from Georgia Tech professors who developed a method for a low rank minimization problem. So it may have tremendous potential in data acquisition. For example, yeah, or you can go up. This one is go down. Oh, okay, yeah, this is good. So for example, you have a sampling matrix that you know only, say, 30% of the data. And the question is how to recover the rest, the missing data. Well, if the data was random, then you can say there is no way you can recover it. But the point is that the data is not random, that there are connections, there are relationships between the data that we see and the missing data. It's like if you heard about Netflix problem, that you want to figure out what are the ratings of the movie, or what the user will, which movies some user will like. So this is exactly the same idea. You want to figure out what is in the missing part. And the approach we were using is about rank minimization. So it should be on the next slide. Over here, yeah, this is the data in Fourier space. So it's one frequency of the data. The data itself is really huge. It's like several terabytes. But this is just one small slice, and you can see the left-hand side has very little data. It may be even just 20% or 15% of the data available. And then you apply the reconstruction process, and you get a picture which is pretty close to the real one. So this means that in practice, we can reduce the number, the amount of the tools that we use for the measurement, and it can save really a lot of money. But this is still in progress, so we are not yet deploying this model to the real data. That probably in the next few months we will do some tests in new data, for the new data. Okay, yeah, that was the last slides. So I'm ready for your questions.
Perfect. So we just thank you so much for sharing those slides with us. We compiled some questions as a SciAm student chapter, and I was hoping to go ahead and get started with a few of those. Is that okay?
Oh, sure.
Perfect. So knowing that you use machine learning for big data, why wouldn't you, or what would you do with smaller data? Why is machine learning not as suited to be used for smaller data?
Well, it depends how large is small data. If you have a few hundreds of observations, this should be considered as small data, right?
Yeah, that probably so. That's what I'd say.
Yeah. You can still use machine learning. I would say machine learning quite often is confused with deep learning. Like when you use neural networks, this usually works with very huge data. But you can use much simpler, less sophisticated methods. For example, you can use clustering, you can use nearest neighbors, you can use some generalized linear models, which will work very well for a small size of data.
Gotcha. Okay. Next one we have is how much, if any, coding languages do you use, and do you ever use languages like Mathematica or MATLAB? Maybe which ones are most important?
Well, I would say MATLAB is more important than Mathematica. I use R language and Python most of the time. Also, Jupyter Notebook is usually very convenient. If you like Mathematica, you can use Jupyter Notebook. You essentially use Python language, but the interface is very similar to Mathematica, where you can write down a few lines of code, run it, and get the output. So it's step by step. It's very convenient to implement.
Gotcha. So as an undergrad, which courses did you find most applicable to your career today?
Oh, as an undergrad, probability theory. I would say some engineering courses may be very, very useful.
Gotcha.
Yeah.
Any courses that you took in PhD program, like did you apply anything towards your job, like when you were in Iowa State?
Well, in Iowa State, the last course I took was Introduction to R. This was this amazing course. I am using R basically every day. For the math majors, stochastic processes is very good. Differential equations.
Yeah.
Yeah,
So
numerical analysis as well. Numerical analysis was really good.
okay.